So today we're going to go over chapter 4.3. We're going to look at electron configurations. An electron configuration is just a way to represent the arrangement of electrons in an atom. So last time we looked at the energy levels in an atom. We have the nucleus surrounded by the energy levels. So this was energy level 1. And it has just one shape orbital, and that is the s orbital. So this is 1s. Then we have energy level 2. Okay, energy level 2 out here has two different shapes, so we're going to draw them as these two separate rings, but they're actually different shaped orbitals. Okay, and they are the energy level 2, s, and then p orbitals. Okay, remember S is a sphere and the p orbitals look like a figure 8 shape. Okay, then energy level 3 out here is going to have three different shapes, or kind of like sub-levels here. So there's our S and here's our P. And the third shape is the D orbital. So energy level 3 has three different shapes, S, P, and D. And they're all very close together in energy. So energy level 3. Okay, and then lastly, energy level 4 out here. Okay, and the energy levels actually do get closer and closer together as you go out, which complicates things, as we're going to see. Okay, they're closer together in energy and closer together in distance. So the electrons start to do some complicated things. Pretend these are nice, pretty circles here. We have to use our imaginations. So there's 3s, 3p, here's 3d. And last but not least, we're going to draw, I said 3s. This was 4s, 4p, 4d, and then 4f. I knew I said that wrong because there is no 3f. Okay, so that's energy level 4. And 4 has four different shapes. I skipped the 3. We'll come back to that. The first ring in every energy level is S. The second ring in every energy level is going to be P. So this is 3P, and this is 4P right there. And then we have D. So 3D right here, and 4D right there. And lastly, 4F. So energy level 4 is the only one on our drawing here that has this F orbital shape to it, because it's the first one that has all S, P, D, and F orbitals, since the energy level tells us how many different shapes there are. So energy level 1 had one shape, energy level 2 has two shapes, energy level 3 has 3, and 4 has 4 shapes. Okay, S, P, D, and F. And in fact, let's draw those again. So we had S was a spherical shape. Okay, pretend that's a three-dimensional sphere. We had P, which looks like a figure 8, and there are three different orientations of these. And then we have D, which has 4 equivalent lobes, kind of like that. And last but not least, we have F, which has a crazy shape to it, something like this. There's actually a bunch of different ones. Go look those up. And the number of electrons that each of these holds is S can hold 2 electrons. P, all three of them combined, holds 6 electrons total. D, remember there's 5 different shapes or orientations, and each holds 2 electrons for a total of 10 electrons in the D orbitals. And F, there's 7 different shapes, each holds 2 electrons for a total of 14 electrons in the F orbitals. So as we're filling up these rings, this is very similar to our Bohr model. We're going to fill up the ring and then move out, fill that ring and then move out, except now we have a little more added onto it where we have these different orbital shapes in each energy level. Okay, let's do some examples. So for lithium is a very simple atom. It has 3 electrons. It's going to have, let's draw it right here. We're going to use this as our training wheels for now. And you guys know training wheels, you cannot keep them on if you want to advance in riding your bike at all. So we can use this for a little bit, but then we're going to have to get to a more sophisticated model. But this is our training wheel for now. So lithium has 3 electrons. Okay, this is lithium. It has 3 electrons. 2 of them are going to go in the very first energy level right here in this 1s orbital. Let's draw them as red. So here's my 2 electrons in the 1s orbital. And then we have 1 more electron to add. It's going to have to go in the second energy level. And it's going in this very first ring, which is the 2s shape. Okay, so the last electron goes right there. And so if I wanted to write out what we just drew, I would write the energy level of 1. So this is my energy level. And then I would write the orbital shape. This is the orbital, okay, shape of S. And then I would put how many electrons are in 1s. Well, there are 2 electrons in that 1s. So this last number is the number of electrons in that orbital. Okay, and that's not all. I had 2s, so 1 electron in the 2s. So 2s1. So there's 1 electron in the second energy level, and it's in the s orbital shape. This is the full electron configuration for lithium. Okay, our next example is sodium. And remember that sodium had 11 electrons. So we're going to add them to each ring up here until we get to 11. Okay, so let's do that. I would have 1, 2, now that ring is full. 3, 4, now that ring is full. I'm going to move out to this 2p orbital. And remember, the p orbitals hold 6 electrons. So I can put 1, 2, 3, 4, 5, and 6. And you guys remember that in 8th grade, you learned that there are 8 electrons in the second energy level, and we drew them as one ring with 8 dots. Okay, that wasn't wrong because the second energy level does hold 8, but now we know a little more detail that it is 2 in the s orbitals and 6 in the p orbitals. So we would write what we have so far for sodium. I have 1s2, there was 2 electrons in that first energy level, and then I had 2s2 because it was filled, and after the 2s comes the 2p, and there were 6 electrons in that 2p orbital, okay, in all of the p orbitals combined, the x, y, and z together. Okay, now this is 4 plus 6 more makes 10. I have 1 more electron, and let's see where it goes. Okay, since I filled up the 2p orbital, I have 1 more electron to add, and I cannot fit it in this energy level. So I have to move out and put that 1 lonely electron out here in the 3s orbital. So our last little bit of our electron configuration is going to say 3s1. Whoops. And that is the full electron configuration for sodium. Okay, fluorine has 9 electrons total. I'm going to use what I have up here to write this one out. So it would be 1s2, 2s2, 2p, and I'm going to stop there. I have 4 electrons, and I have 5 more that I need to add. Remember, this 2p can hold up to 6 electrons, but I only need 5. So this is the full electron configuration for fluorine. Okay, we have a few rules to learn. The off-bow principle tells us that an electron occupies the lowest energy orbital that can receive it. So we are not going to jump out into this top energy level before I've filled all the energy levels before it. Okay, so they're going to fill from this inside ring out. It's kind of like a hotel. This is a strange analogy, but it works, trust me. It's kind of like a hotel that fills from the bottom up. Okay, so we're not going to move up to floor 2 until floor 1 has been filled. And then we fill up floor 2, and then floor 3, and then floor 4 is filled last. So we fill from lowest energy to highest energy. In our hotel, it might be lowest price to highest price. All right, so that's the off-bow principle. The Pauli exclusion principle tells us that no two electrons have the same set of quantum numbers. So if you have the same energy level if you have the same shape, like in the p orbitals, and the same orientation, like px, for example, let's do energy level 3, px. If I had the same energy level, the same shape, the same orientation, the last possible quantum number that can be different is the spin. So if you have 2 electrons in this 3px orbital, one will be spin up and one will be spin down. Sometimes we write them like this as a full arrow. Sometimes we write them as a half arrow to be lazy. This is spin up and this is spin down. Okay, so if they're both sharing the same orientation of the same shape of the same energy level, one will be spin up and one will be spin down. That is the Pauli exclusion principle. And lastly, Hund's rule says that each orbital of a particular energy level gets 1 electron before you pair them up. So for example, if I had my px, my py, and my pz orbitals, okay, so px, remember that these actually overlap, py, and then pz is coming out at us and going back into the board. Each of these is going to get 1 electron on its own before you start pairing them up inside these orbitals. It's kind of like if you have a house with multiple bedrooms, you're not going to have siblings share a room and have empty rooms. Everybody wants to get their own. Electrons are negative, they repel each other, they each want their own. And then once I've run out of empty orbitals, then they're paired up, and spin down inside these orientations. We're going to see a lot of examples of that in a minute. Okay, let's do titanium because this is going to force us to take our training wheels off. Titanium has 22 electrons. That's the biggest one we've done so far. So if I go back up to my rings, I'm going to see I did sodium. So there's 10 electrons here. This is 11. I'm doing titanium now, so I'm going to add 22 electrons to my picture. So there's 12. Now the 3s is filled, and I'm going to come out and fill the 3p with, it's 6 electrons. So there's 1, there's 2, kind of hard to see, 3, 4, let's do 5, and 6. So let's write what we have so far. We have 1s2, it's filled. 2s2 is also filled. 2p6, 3s2, and then we filled up the 3p with 6 electrons. So this is 10 plus 8. I have 18. That means I have 4 more electrons to add. Here is where things get weird. So you would think, following our nice rules that we've told the electrons they should follow, that it should go into the 3d orbitals. But when you get out to these high energy levels, the amount of energy in these starts overlapping. Okay, and the electrons don't care about our nice patterns of our 1, 2, 3s, and 4s and our SPDs and Fs. They're just simply going to look for the lowest possible energy that they can occupy. So what it does is it's going to skip over the 3D altogether and fill in this 4s orbital. Okay, so it jumps the 3D and it fills in the 4s with 2 electrons in it. Okay, but I said we had 4 more electrons to add, and that's only 2. So the last 2 electrons, now, once the 4s is full, it's going to go back and fill in the 3d. So 3d2 is the last part of this electron configuration for titanium. Okay, so that is the electron configuration. Now, once we go on past that, we would fill up 3D, and then where do we go? Where do we go after 3D? If you said 4p, you're correct. What about after 4p? What would be filled after 4p? If you thought that it would jump over the 4D and fill in the 5s, you are correct. So it would jump over, fill in 5s, and then come back to the 4D, and it does all kinds of craziness from there on out. So here's the good news. The good news is we have another tool, so we don't have to memorize all of the jumping about business. We can use this diagram down here to tell us the order, the correct order that the electrons will fill up the orbitals in. And this is what we're going to use for these electron configurations from now on. So we're losing the training wheels. There are 3 ways to denote electron arrangement. We are going to use this figure right here, and I'm going to draw in turquoise the order. So it starts with 1s, just like we have been doing. After 1s comes 2s. Okay, and we're going to go in these diagonal lines all the way down. You'll see the pattern. After 2s comes 2p, and after 2p comes 3s. Okay, and then after 3s, 3p, and here's where it starts skipping around. Instead of going to 3D, it fills up the 4s and then comes back to 3D. Okay, and then 4p, and then 5s is filled. So follow the diagonals to fill these up before you move on to the next line. After 5s is 4d, and then 5p. My line got a little squiggly there. Okay, so it goes 4d, 5p, then 6s, and you guys can see the next line would be 4f, 5d, 6p, 7s, and then 5f fills up, followed by 6d, and 7p is where our periodic table ends. So all of these filled up to 7p is 118 electrons. There's only 118 elements, so that's where we stop. Okay, so follow these diagonals to write our electron configurations from now on. This is our new diagram, and this one's a lot easier to remember. All of the s orbitals, remember they hold 2 electrons before they're full. All of the p orbitals will hold 6 electrons, and then they're filled up. The d will hold 10 electrons, and then they're full. And then lastly, the f holds 14 electrons. Okay, so we're going to use this with this knowledge to do our electron configurations from now on. Let's do some more examples. So let's do chlorine. Using our picture above, it has 17 electrons. Starting with 1s, it has 2 electrons there. 2s also holds 2. After 2s, we fill up 2p and then 3s. 2p. The p orbitals hold 6 electrons, so I'm going to fill it up. And then 3s holds 2. Okay, where do we go after 3s? 3p, that's right. 3p, and let's stop and pause. This is 10, plus 2 is 12. I have 5 more electrons, and this can hold 6. So the last little bit is 3p5. Okay, so that's the electron configuration for chlorine. We are going to do bromine and sulfur. Bromine has 35 electrons. Okay, so bromine has, let's do it in purple, 35 electrons. I'm going to use what I have here and build on that. So I have 1s2, 2s2, 2p6, 3s2, 3p6. That's 18. I have a lot more to go. What comes after 3p? After 3p is 4s, and then after 4s is 3d. So 4s, 2, and then we said 3d, and it can hold up to 10. Okay, let's stop and count our electrons and make sure we didn't go too far. That's 10 plus 10 more, because 6 and 4 is 10. So I have 10, 20, 30. I have 5 more electrons to place. And what comes after 3d in my chart? After 3d is 4p. P, it can hold 6 electrons, but we only have 5. So it is 4p5. That's the full valence electron for bromine. Okay, and let's look at sulfur. Sulfur is an easy one. It only has 16 electrons. Okay, so sulfur has 16. Let's see if we can do it using what we have so far. Sulfur is going to be 1s2, 2s2, 2p6, there's 10, 3s2, there's 12. I have 4 more electrons, and they're going to go in the 3p orbital. Add up the number, and I get 10 plus 6 is 16. So this is the full the full electron configuration for sulfur. All right, we're going to pick up on orbital notation next. You guys can see the next video for orbital notation and noble gas notation.